section. It's not going to be on your test unless it's a bonus, but we're going to use it on Friday to do the hot cocoa problem. So you should have for this one, if it's a half-life, right, and it lasts 14 days, your first step is to set it up like half-life. I start with 100, I end with 50. I don't know K, but I knew that it took 14 days. So you should have divided by 100. So now you've got 0.5 equals E to the K times 14. Change it into log form. So you're going to take the natural log of a half and then divide by 14 to get your final answer for K. So what did we say that was? So the natural log of a half divided by 14 is negative 0.0495. Some of you, I think, just put negative 0.05. Did you round? Yeah. So then you didn't do the natural log of a half divided by 14. I know you verbalized it. Oh, there's two parentheses and not everything is tripping you up. Oh, because I think you put this whole thing in the parentheses. Oh, that's weird though. But one extra parenthesis would do that. Okay, so now we want to know if 35 days have passed and we currently have 80 grams. So see how I use two circles for the first part of the two squares I'm going to use for the second part. So you're going to plug 80 in as your initial value. You're going to use your K value and you're going to use your T value and type that into your calculator. You don't need the table function for this. Just go ahead and type in that star, 80e to the negative 0.05 times 35. See what you get. See the 35 days, yeah. So you're using the information. To me, this is the easier part of the problem, is you're just plugging everything in and getting an answer. The hardest part is solving for K. So a lot of you are doing really well on setting this up and solving for K. This is the hardest concept of the whole test. So if you can do it on an application problem, you should be able to do it when it's just they give you the equation and you put it in log form. So that's really good. I'm happy that you guys aren't like brain dead the day you get back. You're doing like the hardest calculation the day you get back. So that's really good. Oh, what did this come out to? 80 e to negative 0.05 times 35 days. 13.9 or yeah, 14.01 if you use the whole K value. Yeah, 13.9. Yeah, if you use the whole K value, you actually have a more exact answer. This times 35. Yep. So see how 13.9, 14.1, yeah, depending on if you rounded or didn't round. Okay, I want to show you Newton's. Well, you should be showing me what your K value was. So I'll see that you rounded your K value to this correctly and use the K value here. So to me, this would be correct, but you showed that that was your K value. Okay, Newton's law. I want to show you this so that we can use it on Friday. So turn back to page 409 that we were on and take a look at this Newton's law problem right here. And it's the same process, but it's a slightly different formula. So U of T, yeah, Newton's law of cooling. Capital T plus U sub 0 minus capital T e to the kt. So here's e to the kt right here, right? E to the kt is right here. This information is taking into account the initial water temperature, right? Because that would affect how fast it cools. The capital T is the room temperature, because if you just set your hot coffee in a 70-degree room, or if you set your hot coffee outside in a 20-degree, cold day, where's it going to cool faster? It'll cool faster outside. Or do you ever take something and put it in the refrigerator to cool faster? So this is the surrounding temperature. It affects the K value. But that makes this look a little bit more overwhelming. So this is just room temperature. This is the final temperature of your liquid. So after 10 10 minutes, this would be like the final temperature after 10 minutes. So we're going to use it and find K the same way that we did with the other function. So this says Annie boiled water for tea. If you boil water in Celsius, how many degrees is the water? Does anybody know that fact? Water boils at, that's when it freezes at 0. It boils at 100 exactly. So it actually makes more sense in Celsius. In Fahrenheit, I think it's what, 212? Yeah, but that's Fahrenheit. So Fahrenheit boils at 212, freezes at 32. Celsius boils at 100 and freezes at 0. So Celsius is kind of based on like water, right? Okay, so this is kind of the boiling water is telling you that it's starting at 100 degrees Celsius. I would tell you what it was in the problem. But, so now it says he waits 10 minutes, and now he found the temperature of the tea is 60 degrees Celsius. So this is as far as I want to go for now. I need to figure out the K value. This is important for restaurants. They need to know if the soup is this temperature, what's the safe temperature for serving it to a customer? You know how they have the heat lamps? They need to know what temperature it goes out to the customers. Dunkin' Donuts needs to not sell scalding coffee anymore because you remember the court case, someone spilled it on themselves and scalded themselves with like second-degree burns. So you have to know how fast it's going to cool in the container to make sure that you're within your legal serving whatever temperature. So we're going to use Newton's law of cooling to figure out the K value so that we can figure out if Danny likes the tea at 40 degrees, how much long should he wait? Same thing with our hot cocoa. When I boil it to 100 degrees, you're not going to want to drink it. So we're going to do a little experiment and figure out how fast does it cool in a MOV or a turbis with a cover, and then we're just going to enjoy our hot cocoa separate from the experiment. But so let's fill in the information. U of T is what the final temperature of the tea is, and that would be 60. So 60 equals, what is room temperature? I guess I need this piece of information down here. Room temperature is 21 degrees Celsius. That's about 70 degrees Fahrenheit. So I'm going to put a 21 for my capital T, and then I write plus, and then in the parentheses, you write your original temperature minus your room temperature. So I'm just following this formula. Then I write E to the K times T, and we know that T is 3 minutes. So that's the hardest part of Newton's law, is putting the right pieces of information in the right variables because they all have T's. So I would give you this whole description. So for on the test, this will be a bonus question on Newton's law, and I will give you all of this information. You don't have to have it memorized. It's just using Newton's law to get the answer. So now I'm going to solve for K using order of operations. So your first step is to, let's do the parenthesis first. So what is 100 minus 21? 79 times E to the K times T. Here's the biggest part where people mess up. They like to add the 21 and the 79, and you can't do that. The 79 is attached to the E. So your next step is to subtract just the 21 to the other side to solve for K. So we're going to subtract 21 to the other side. That gives us what? So 39 equals 21 to the other side. 60. 60 minus 21 is 39, right? Nope, the 79 is still hanging out. The 100 minus 21 gave us the 79 right here. This was subtracting 21 to the other side. Now, this problem looks just like all of our half-life type problems, right? Divide by 79, change it into log form, and solve for K. So I think if you could get it to this format, that should look like all of the problems that we just did before lunch. The hard part for Newton's law is just getting it set up and not messing up the order of operations. So I'm going to divide by 79 on both sides of the equation. I don't know what that is, but 39 divided by 79 is 0.49 is good. 0.49, or you could leave it unrounded in your calculator, equals e to the k times 3. Change it into log form and solve for k. Yep, natural log of 0.49 equals k times 3, because the base snuck in there is e. E to the k times 3 is 0.49. So take the natural log of 0.49 and divide that by 3, and that will be your k value of how fast it's cooling. I got negative about 0.23 or 0.24. I guess I should round it. We've rounded a couple times, so we'll be off by a little bit. All right, so that's my k value. Now, if you wanted to type it into the calculator, or now we need to solve for the time to get it to a certain temperature. I guess we're gonna have to do it the long way. Typing this into the calculator won't help us too much. Sorry, you might be out of room. Let's see if I can write onto the next piece of paper here. All right, now to use the K value, what is the temperature I want it to get to? I want to get it to 40 degrees, right? So 40 is my new ending temperature. Room temperature hasn't changed. And it says, how long should he wait before drinking his tea? He's already waited 3 minutes. We need to see how many more minutes he needs to wait. So what's the starting temperature of the tea? The tea is starting at 60 degrees, right? So I'm going to put 60. So I've got, it's cooling to 40. Here's room temperature, and here's my starting temperature. 60 minus 21, because that's room temperature. E to the K was negative 0.24. You need me to zoom it in a little bit? So 40 equals 21 plus 60 minus 21, E. There's my K value. I'm trying to find T. See if you can model it the same way. Subtract, divide, change it into log form, and solve for T. See if you can do that last one. So maybe I'll save one Newton's law problem for tomorrow. What would you have to do? You're going to try this one. I'll put the answer up in just a minute. Oh, 410 had one Newton's law problem on it, right? Did you guys do the front page of 410 though? All these application problems? You remember doing that? So you successfully did 410, but you did not do 411? I did. I did. Okay. So that's what we should do Monday and Tuesday, right? Yeah. I didn't leave you a quiz, right? You guys can do a quiz. Right. Okay. Everyone, questions? Yeah. 4, 3, and 4, 4. Can you check my homework? Yeah. Yeah. Finish. Try this one. See if you can finish that one. Let me just close this real quick.